I've been doing a number of projects for Mike's Lionel Trains Electronics that have used timers, specifically the integrated circuit 555 8-pin dual inline chip. Here's a close-up of the 555 timer chip being used in the system I have built. One thing in common to all of my projects that use the 555 is the importance of the resistor and the value of the capacitor. Measuring the resistance is an easier task, being the capability of analog resistance meters or analog multimeters for many years in the past. But measuring the capacitance is a greater challenge, with there really being no capability, no affordable solution until more recently with the availability of digital multimeters. With the advent of the digital multimeter, such as this particular one, there comes the capability to measure the value of the capacitance with test equipment that is affordable to most people, say less than $100. This becomes important if the writing on the capacitor is too small or too hard to read, or if the electrolytic capacitor is older, as capacitors can deteriorate with time. Here is a demonstration of the capacitance checker capability on my digital multimeter. Start by turning on the power, and let's see, and our setting is already on the capacitance. So we've got voltage, ohms, and capacitance here as some of the main functions. Alright, let's start with a smaller capacitor. First thing you do is make sure you identify the negative side polarity, and it goes to ground, goes to the black lead, and the other lead goes here. And we watch what happens, make sure the leads are separated, and we're reading 20.5 to 20.53 microfarads, and given that this is a 22 microfarad capacitor, that's a pretty accurate reading. Alright, let's try another one. I've got the minus here, and whoops, the minus goes to the black. Messed up. Okay. And plus goes to the red, and let's see what happens. Okay. It's at 9 nanofarads. Okay. Here we go. Okay, finally, it took a while. I had to think about it for a while. 98 microfarads, which is a very good representation for measurement of a 100 microfarad capacitor. Now watch this. This is going to demonstrate that a digital multimeter like this can only check capacitances so large. This one I know happens to be a 220 microfarad. Okay, let's wire it up and see what we get here. And we wait, 144 nano, and we wait. Okay, and now it's gone to 0 L, which is the indication that it cannot do the capacitance measurement on this 220 microfarad capacitor. So this thing's limited to about an upper range of 100 microfarad capacitor testing. Let's take a look under the hood here of my capacitor checker. First thing is that it operates from a 12-volt switching power supply purchased from MCM Electronics with a capacity of 1.5 amps. And we plug it into the wall. I plug this in. Whoa, this isn't screwed together. And I plug this in, and you see that there's a power supply on light here. Then there's a start button that starts the timing cycle, and there's a 7-position switch that gives you a choice of the range for capacitance, and then there are terminals at this end for connecting the capacitor under test. I'm going to unplug it. If we look inside, what we have is first a circuit board with the 555 chip, also a 10K pull-up resistor, and a relay that lights the light while the timing cycle is on. On the inside, we have this array of resistors that you select with the 7-position switch and determine, and it determines what size of capacitor you're trying to test. And then here is the green timing light to indicate that the capacitor is under test. And here is the table of equation. And here is how it operates. The red light's on, so we know we've got voltage. We have our 7-position switch, and at this point it's in the E position. The start button and the green light button for the timing cycle. And a capacitor, a larger capacitor, has been connected between the black and the red terminals. So what we do is start the cycle, start the watch at the same time, and see if we're on the right range or if we have to adjust what range we're on. Typically, we want to have time between 5 to 15 seconds to allow us to accurately evaluate the capacitor. Now this one's getting pretty long, and we're up to 30 seconds and it hasn't gone out, so we're going to have to, what you do is if the time is too long, you go clockwise. See what's here? And this is now the F position, and resetting the watch. And we'll try again. We're now in the F position, and the resistor is a 3.3K. Okay, 15.3 seconds. That's a very usable amount of time, and so we're on position F. All right, now we compute the capacitance. Our setting is F. We're on the F setting. Okay. The equation for the F setting is C is equal to 315 times T, the time, and the units are in microfarads. Time was 15.3 seconds. Okay. So our computed capacitance then is equal to 315 by 15.3 and 18 or 4819.5. Okay, microfarads, and let's come over here. We can call it 4820 minus 47. Oh, the value on the capacitor was actually 4,700 microfarads. Okay, so the difference was 120. And if we do 120 over 4,700, it comes out to be about 2.5%, which is really pretty good. Well, let's run another trial, one more trial. And as you see, there's two ways to connect capacitors to it. For small ones, you can use these two terminals, and for larger ones, you can attach an alligator clip lead on that one. And in fact, the last one, that's how we did it. All right, so we've got a capacitor in there. Let's assume if we go on the E setting. Okay, did you notice how quickly it timed out? And that's way too short to be able to get an accurate reading out of it. So if it's too short, you go this way, you do counterclockwise, one position. And I think we're now in the D position, and let's see how this does. Okay, that's a usable time, I think. So reset the watch, and away we go. Well, that was still pretty quick, 3 seconds. Try that again. Okay, less than 3 seconds. Okay, all right, let's go to the C position. Okay, 5.6 seconds. That is definitely a usable value. For the C setting, our resistance is 100K. The equation is C is equal to 8.6 T microfarads. Okay. T is equal to 5.6. Okay. So C is equal to 8.6 times 5.6 microfarads. And compute 48.2 2 measured microfarads measured. Actual. Okay, let's compare the measured and the actual. The measured is 48.2. The actual is 47. And it gives me a difference of 1.2 microfarads. And so our difference is 1.2 over 47. And that is very close to 2.5%, which is very respectable accuracy. This is a table of the resistances and the equations used to compute the capacitance for each setting. This is the schematic for the capacitance checker. Notice there's a 7-position selector switch with 7 resistors, the 555 timer, and the relay to control the green light. Bye for now. Thanks for watching.